Good morning, folks. This is the video solution for the homework on week 5, lab 5, and it's for the 8:30 class. Now, it's a problem from previous midterm. However, the wording, I have changed it a little bit because the way it was worded before, it was not quite what I intended to do. So here's the problem. You have a structure like that. As soon as you see this, one thing that you have to realize is that this problem needs to be done as a hybrid problem or hybrid mesh problem. In other words, the cylinder in the middle has to be modeled with solid elements. This kind of relatively thin structure should be done with shell, and the side support should be done with beam elements. You should not go ahead and just because you see here resembles a solid object, you go ahead and create a solid object of this type and solve the problem. It has to be hybrid. Now, the way it is that these endpoints are clamped. These at the ends of the bars or beams are clamped, and this thing in the middle is fully bonded or perfectly welded to that sheet. And that's what we mean by a fastened connection. Now, notice that the way, and this whole thing is subjected to a gravitational pull of almost 10 G. This 10 G, G in imperial unit is 386 inch per second squared, so 10 G is roughly that number. Incidentally, the pull of the sun is 170 times 77, almost 77 times G. So this is a massive planet we're talking about to have that acceleration. Now, in the past, I may have said that this is accelerating in the indicated direction as 10G. That is not quite correct the way it's worded. What I intended to say is that it's subjected to a gravitational pull of magnitude 10G. The other thing is that because of the way this is all presented and worded, notice there is some kind of a ambiguity here. In other words, this height, for example, 2 inches, is it from the surface, top surface of the sheet, or is it from the middle surface of the sheet? Because we are assuming that this is shell element, and in a sense it is relatively thin, 0.1, doesn't make that much difference whether I would take this height to be 2 from the top or 2 from the middle surface of the sheet. I mean, in problem where these may be critical, obviously you have to extract the middle surface and then exactly say what is the height of that cylinder. So either way, if you did 2 or actually 2 minus 2 from the surface, top surface, or 2 from the middle surface, both are acceptable to me. Now, let's go ahead and do this. So incidentally, these hybrid problems can be done as an assembly or as a single part. I will do that as a single part. It can also be done as assembly, and I think, if I'm not mistaken, I did one problem for you in the class where actually it was done with the part as a single part and as an assembly of 3 or 4 parts. Okay, the choice is yours. All right, let's go ahead and do this. So we start with the part file. Okay, I forgot to say, use as many planes of symmetry as applicable. This is very important. Now, if you look at this problem, it has one plane of symmetry because the direction of the gravity is like that. If the direction of gravity was vertical, then there would be 2 planes of symmetry. But here, there's only one. So you have a choice of making this whole thing and then trying to split it, or just making half of it. That's entirely up to you. I'm going to make half of it. So on that plane, I will sketch. I'll sketch a rectangle, which is 8 inches long. That's going to be the sheet that that cylinder is going to be placed on. Let's dimension these things. So this is 8. And this is half of that width. The width is 4, so half of it is going to be 2. Exit. and fill this thing. Now remember, as soon as you say fill, you're thinking about surfaces. You cannot be in right here, part design. So you have to switch to generative structure. What is that? Shape. Yeah. Shape, generative structural, generative shape design. Right. And that's where you see extrude and revolve and the shaft and the fill, etc. We fill this with a surface right there. Okay. Now, I also want to create these two beams, one on, it doesn't matter how I take it, one on this side and one on that side. Okay. So the one option of making these beams is obviously you need lines here. So I'm going to make my lines like this. So make a line starting from a point and a direction. The point is this point, for example, and the direction is direction X according to what I have here. This is going that way if you look at it. So I want it to go to the other direction, and I want it to go at the length of 1 inch. There we are. And I repeat this thing on that side. Let's see now, direction is X. Yeah. Please note that I need two lines. I don't care how you do it. You can do it any way you want. Now, this cylinder, half of it is sitting over here, right there. So on that face, I will sketch. The cylinder is sitting here, so I'm going to make an 80-degree arc. I mean, we have to clean these. Don't worry about it. We will clean it. Okay. So this point, I want it to be on that line. And there are different ways of doing these things. So let's see, this point, control that line. Coincident. Okay, very good. And I want to bring these things down. This control that line, also coincident. I was not thinking when I was doing this arc, but it can be fixed. Same thing on this side. That point, control that, be coincident. Okay, now if I exit, dimension, this radius is 1. This radius is 1. Okay, exit. I want to pad this thing, but notice that pad is a 3D solid object. You cannot find it in generative shape design. You have to switch to part design, mechanical design, part design. And if I try to pad this thing, it'll come back and complain that this is not a closed curve, because when I drew it, I did not close the bottom edge. So let's go back to that sketch. I'll let you try it, see if you get the error message. Okay, so you go from this point, now it becomes a closed curve, and you can pad it. Exit, pad it by 2 inches. Good. Okay, everything is made out of steel, so I go all the way to the, yeah, this is only a single part, so it doesn't make sense to talk about everything is made out of steel. This part is made out of steel. So you click on the apply material, metal, steel on that part, and that's pretty much it. So this is as far as the model is concerned. Now we're going to go to analysis and simulation, generative structure analysis. Notice that CATIA sees a solid object, immediately it meshes it, it's right here. And I have to mesh the beam and the shell. So to do the shell, it's very easy. You just go there. Well, since the beam is up there already, let me do that. Click on this, select that, and you have to do these separately. Notice that you can't select this one. Okay, so we say okay, and that size is fine. So that means about 5 elements there. And do another one on this side. Yes. Okay, now let's put the cross-sectional properties of the beam. 1D property is going to be on this. And if you notice that it is cylindrical, that's what I want. You click on it. The radius is 0.02. That's what this says. The radius of the cross-section is 0.02 inches. Is fine. We say OK. And if you look close enough, you see actually it's sitting there, the circle of radius 0.02. However, because we zoomed out so much, we can see it from this angle. Do it again with that guy. Same information, and once again, you can see that it's right there, circular cross section. Now, okay, so let's go ahead and do the restraint. So, oh, I forgot to mesh the shell. I have to mesh the shell, right? So this was beam. Here's the shell right there. That's too big, so make it 0.2. Linear. In the absence of any information, take linear elements with default size and sag properties. Now the thickness is right here, 2D property. You click on it, you select that, and 0.1 is the thickness that is described right here. What is that? Thickness of the plate is 0.1. Good. You say okay, and you can look at your mesh now. Right-click mesh visualization. There we are. So you can see the solid element, shell element, and the beam element. Okay? All right. Now deactivate this. So this end is clamped. Okay. And so is that end. In fact, if you zoom in, you see that the clamp sign is there, but you're too far away. And okay, good. All right. That takes care of this. Now, surface slider is on that face because we split it. There we are. We didn't split it, but we made half of it. Now, don't forget to put symmetry restraint on this edge of the shell, because this edge of the shell is on the symmetry plane. So, and don't forget that in order to put the restraint, in order to put these things or load, you cannot put it on sketch. There's a sketch sitting there and it's blocking the view. So right click, hide it. Now notice that it turned completely black. That means it's an edge that you can pick. You click on it, you click on that edge, select the user define, uncheck everything, make sure you don't make any mistake. So this lies in the global XZ plane immediately, no translation in Y, no translation this way, Y, and rotations opposite, there we are, and we're good. Okay, now the load is coming from acceleration, right? It's actually gravitational acceleration. You click on it and you select the entire part. You can, whatever you select is going to be the whole part because this is a single part. You click on it, and in the direction X, you have two choices. You can put 3,860 inch per S2, which automatically is going to convert it into meter per second squared because I did not change my unit of acceleration. I can if I wanted to, but I'm not going to do that. That's going to be roughly, this is going to be roughly 98 meter per second squared. You saw that, almost 98, right? Let's go check it out again. See, roughly 98. Okay, good. Yeah, and the symbol for it is in the wrong direction. See, it's in the wrong direction. It should be in direction X. Wrong. So this should go up here. Let me make this thing 0. It was in the wrong direction. It should go up there in the X direction. So 3,860 inch underscore S2. It'll be 98, right? You can see that, 98. Good. And the direction points this way. Now, if I run this thing, it will bomb out. You'll see why. Let's run it and see that it bomb out. So okay, so let's find out why. So if you click on the deformation and animate it, basically nothing is attached to nothing else. Nothing is attached to anything else. So what we're going to do, we have to create connections between them. So let me deactivate this plot. We discussed these in class. The end of this line and the corner of this sheet, there is a connection between them, and that connection is rigid. So here's what we're going to do. We're going to say first one, and I'm going to call this thing end or corners one. How about that? Corner one, so that you know where it is, because there's going to be two of them, corner one and corner two. So for one component, I can hide this line, select this point. See that vertex? For the second component, I select the end of this line. Now, if I'm not sure, I can bring this thing to the front. I can hide that and select this point. Definitely it's from this, okay? Say okay. So that's this corner. Let's do another one. On the other side, the order is not important, so I start with this second component, the corner of that. Let me bring this thing to the front and hide this and select that point. Now, if it's blocking your view, it won't let you do that. Here's what I suggest. Put the cursor on it, right click and hide. Oh, undo. I want to hide that connection because blocking won't let me pick that, right? It won't let me pick that. So let me do the following. Let me hide the second one that I'm trying to do. Hide it. Now I'm going to go and select that. It can happen. And incidentally, I'm going to call this thing corner 2, right? Corner 2. Okay. So it's there. It's just that it would block my view, won't let me pick that corner. Good. Now, by the way, this line isn't hiding. If it's bothering you, you can bring it in the front. It's there. It doesn't hurt anyone. Good. And I create a connection between the bottom of this and the top of the shell. So another connection, I'll call this thing cylinder and surface. Cylinder, surface. Okay. For the first component, I can hide the surface, although the order is not important. Select this. For the second component, I select the surface. As I said, the order is not important. And then say OK. Let's bring this thing in the front. Okay, so you can see that we created corner cylindrical surface. Now these two, because these are point to point, they must be rigid. So you go to connection property, under distance connection property, this guy, under this guy, okay? And there's a rigid, and that's going to go for the first, and you have to repeat it for the second, repeat it for the second. And notice that when I did this, by the way, when I did that, let me go on the properties, double click on it. Yeah, this is the one that I did. This is the transmitted degrees of freedom. In other words, show me all the stuff that transmits from one things on the beam to things on the shell. And obviously I want all of them to be transferred. And now this is not a cable. This is everything is perfectly welded together. So everything is transmitted. Okay, that's the default. You say okay. And then this one is fastened. This one, the bottom of the cylinder and the top of the shell is fastened. So go for face connection property. Find the fastened one, which is right in the third one from the left. Select that, and we say okay. See, it puts the fastener sign here, and then run it. Hopefully, you didn't forget anything. Okay. Now, because this is a gravitational pull, it should go this way. Okay, in general, it should sag down because it's like this, right? The gravity points down. So let's check it out. Change the scale. We can't see it because we interrogated CATIA to tell us what went wrong. So click on the scale, default, there we are, okay? And you can animate it. If this thing was actually on hanging on the in that planet like that, gravity pulling pointing down, and you animate it, obviously this is the motion, the way it's going to go. It's going to sag down. Now you can also look at the, for example, the displacement. Very little, very little. Actually, 0.02 is not very little because that G is pretty high. Yeah, the G is very high, and I mean, obviously, you can do it like this. Yeah, and von Mises stress, of course, if you want it, right here. Notice that it doesn't show much stress in this solid element because this is pretty much massive piece. So double click on it and say, okay, on this selection, show me that solid too. So that would be the solid one, which is, where is that? There. This is the first, but this is the part, right? Cylindrical. And you say, okay, you can see that there are stresses primarily at the very bottom because the rest of it is kind of moving as a rigid body, but down here it has contact with the or attached to the welded to the surface. So that takes care of this problem. Good luck.